So, well, everything does only have two forces on it. Remember that you know that everything's a two-force member if there are no weights included and every load is just applied at the joint. So let's start numbering these. I'll call it 1, 2, 3, 4, 5, 6, 7. So we know we're going to have a system of 7 equations. And then for joints, I'll call it A, B, C, D, E. And everything's 20 degrees. Okay, so I'm going to start out by, we don't care about the reaction between the ground and the pin at A, so I'm just going to jump right to B. So free body diagram of B. We have 400, F1, F3, and F4. And so Newton's second law says 400, 0, plus negative 0.94 F1, negative 0.342 F1, plus F4, 0, plus 0.94 F3, negative 0.342 F3 is equal to zeros. So that's two equations. I'll start out by writing out the equations, but then, so our first equation here gives us negative 0.94 F1 plus 0.94 F3 plus F4 is equal to negative 400. And the second equation says negative 0.342 F1 minus 0.342 F3 is equal to 0. So if you wanted to solve it by hand, we could start to simplify it already. I mean, I think this is going to be a big enough system of equations that we probably just want to use reduced row echelon form. So now we'll go to C. And that has F2, F3, F5, and F6. And that is everything on that joint. So negative 0.94 F3, positive 0.342 F3, plus negative F2, 0, plus 0.94 F5, 0.342 F5, plus F6, 0, and so this is negative F2, minus 0.940 F3 plus 0.94 F5 plus F6 is equal to 0. And equation 4 says 0.342 F3 plus 0.342 F5 is equal to 0. So that's 4 equations. And then joint D. 4, 5, 7, and 620. Okay, so 620 down. And then I forgot already. 4. So F4, F5, and F7. So Newton's second law, we have negative F4, 0, plus negative 0.94 F5, negative 0.342 F5, plus positive 0.94 F7, negative 0.342 F7, plus 0, negative 620 is equal to zeros. So equation 5 says negative F4 minus 0.94 F5 plus 0.94 F7 is equal to 0. And equation 6 says negative 0.342 F5 minus 0.342 F7 is equal to positive 620. And we just have to do one more. That's at E. So F6 is this way, horizontal. And F7 is this way. And then because it's a roller, we have a force that's perpendicular to the wheels, to the ground, pointing towards the body. So I'll call this RE. And so we have negative F6, 0, plus negative 0.94 F7, positive 0.342 F7, plus 0 RE is equal to zeros. So equation 7 says negative F6 minus 0.94 F7 is equal to 0. And equation 8 says 0.342 F7 plus RE is equal to 0. Yes?
So the reason you didn't do A was because it would add 2 variables?
It doesn't add 2 variables. It's still, well, yes, exactly. Yes. So it doesn't add so it doesn't add any more members. So, and it introduces two new variables that we don't need to calculate anything about the members. Yeah, exactly. Anybody want to see me go through reduced row echelon form, or y'all feel good about that? Okay.
So how do you generally determine like what joints you should be doing your free body diagrams of?
Yeah, well, you can do them all, and then we would have just had 10 equations for 10 variables. The two extra equations would just be the two components of the reaction at the ground.
Okay.
But I guess in this kind of thing, if you have a fixed joint with the ground, you might as well leave that off. But, you know, I mean, there are reasons that it would be useful to calculate those reaction forces, just not for what I asked in this problem. But the only way, so if you're trying to figure out if a structure, if you can use the truss simplification or if you have to use a full method, you can use the truss simplification as long as the members don't have weights and all of the external loads act at the pins, including the reactions with the ground.
So then would all these members have the same magnitude of force on the ends of them? Or would it work out to be different?
I think it's all different.
Okay.
You know, always it seems like some repeat, but the fact that you have these two different external loads acting and stuff, I think they'd be pretty much different.
Okay.
And you'd see that some have really big tensions and compressions and some have pretty small ones. And that would be important, obviously, if you're choosing the material or the cross-sectional shape for these members. Any other questions about that?
What's that, RE again? The variable?
What is it? It's,
yeah,
that is, so this, I'm kind of thinking of what I'm drawing the free body diagram of at E is I'm kind of jumbling that whole roller in as the pin. Okay, and so the forces we have acting on it are
Oh, so it's just the roller. That's what.
yeah, that's the force from the ground onto the rollers.
Gotcha. Thanks.
Yep.
So roller E, joint E.
Right.
Gotcha.
Any other homework questions you want to see? Okay, so now we're going to start getting into internal loads. You guys who didn't take statics from me, did you do internal loads in your statics class?
Yeah.
Okay.
I took mine at Denver Hills. Yeah.
With who?
Denver Hills.
Okay.
Joan Carter.
Okay, great. Have you seen internal loads before?
Oh, it's been a while.
Oh, been a while. Okay, we're going to go back over it, but it's good to know that you've seen it before, you know. So internal loads in beams. So let's say that we have, I'm going to say we have a cantilever beam connected to the wall over here. And let's say that this thing has a length of 1 meter. And external loads over here of 1,000. And this angle is 45 degrees. And then let's say that we have a torque applied to the end of 500 Newton meters. Okay, so has everyone seen that notation for torque before? That, like, what that is a couple. That's why it has the two heads on it, and it's saying that's a couple in the direction according to the right-hand rule this way. So that's twisting this end this way. Okay. And we want to calculate the internal loads at this point A. So what we're going to do is we're going to choose as our free body the piece that goes, well, actually, I'm getting ahead of myself. We're first going to, we're going to calculate, so like step one is we're going to calculate the external loads. So this is just a statics problem. So our free body diagram, we have the force here of 1,000. We have the couple here of 500 Newton meters. And now we have to think about the joint. And this is a fixed joint. So if you remember back to statics, fixed joints apply a full vector of unknown forces and a full vector of unknown couples. So the forces we're dealing with are just in a plane like that. So I'm gonna call this R, that's the reaction force. And then in order to keep this in static equilibrium, there has to be a couple this direction to keep it from bending down. So I'm going to call this, M. So what coordinate system am I going to use? I guess I'll use X this way, Y this way, and Z towards us. So that means that this reaction couple is MR in the Z direction. So that'll keep this 1,000 Newton force from bending it down this way. And then we also need a reaction couple over here to keep it from spinning along the x-axis.
So a reaction couple is a moment?
Yeah, it's right. It's a pure moment. So remember, couples are moments that don't depend on the about point.
Right.
So yeah, so it's a moment that you just kind of add in there. So this is going to be in the x direction. Obviously, it's going to be in the opposite direction, but I'm just going to make my default the positive x, and it'll just come out negative. So this is my MRX. And that's my complete free body diagram. And so Newton's second law says Rx, Ry plus, if I do the trigonometry on this, this is negative 707.1, negative 707.1. The 500 isn't a force, and so I'm going to leave it off. And so this is equal to 0, 0. And so right away we can tell that this reaction force, do the algebra, is 707.1, 707.1.
Do you use reduced rho echelon form for that one?
You could, but in this case, it's uncoupled, so.
I'm just messing with you.
Oh,
It's
I got you. Sorry. Reduced row echelon form would solve that equation for you, though.
I hope.
I guess it's already in reduced form now that I think about it. So now the moment equation, Rn2L, let's do it about Z first, because I'm just used to doing Z more often. I'm going to choose as my about point this point here. So that means that R doesn't produce any moments. It's acting at the about point. The horizontal component of the 1000 doesn't produce any moments. So all we have to worry about is the vertical force. And so we have plus or minus a moment arm of 1 and a force magnitude of 707.1. And now we have to think about the direction of that. Would that downward 707 force make this rotate clockwise or counterclockwise around that about point? Clockwise, so we want the negative. And that is, and then don't forget to put in our couple MRZ. And these add up to 0, and so that tells us that MRZ is equal to positive 707.1 Newton meters. And now we'll do the moments about the x-axis to deal with that torque. So we have MRX plus 500 is equal to 0. And that tells us that MRX is equal to negative 500 Newton meters. Anyone have a feel for how many Newton meters of torque you can apply to like a regular screwdriver? Order of magnitude? I mean, is it 1,000,000 or 1 or 0.001 or?
Probably about 20 or 30.
Oh yeah, that's right. I always say around 10, but that's the right order of magnitude. You're stronger than me, I guess. So these are very big couples compared to what we could apply. Okay, so now we're going to go to step 2. And we're going to do our cut. And we want to calculate this internal load at a specific point. Okay, so if you remember back to working on internal loads, you did it at these using these kind of general cuts that represented all these different values, and you got your answers in terms of x. We're starting here by just making this very specific cut. So the piece that we're cutting, I'm going to, in light blue, draw the part that we're leaving off. Okay, so we're leaving off this force over here, this couple over here. We're leaving off half the beam. What we're including is a force vector. I'll just put it all as components. So 707.1 that way. 707.1 newtons that way. a couple this way of 707.1, and then a couple this way of 500. So that's what's happening at the left end. And now we have to think about what's happening. So our free body only includes the left half of the beam. So we have to include any loads that the right half of the beam, the light blue part, applies to the black part that we're isolating. Okay, so we're going to treat this as it's a fixed joint. So we know it's going to apply a full force vector, and it's going to apply any couple components that we need. I'm going to write this as an internal tension T, a downward shear force V, a bending moment M, about the Z-axis, and then a torque, I'm going to write this as fancy T to differentiate it from the T for tension. Any questions about that?
Can you do that in two separate cuts, or is that the same one? Did I miss that?
This is the only cut because I only asked for what's happening at this line A.
I see.
Okay, so I haven't done any, we're not doing any general stuff yet. We're just doing it for a single place.
I mean, I think there'd only be one cut anyway.
In this case, there'd only be one, that's right.
But if there was like another like external load or something.
Right, exactly. Yep, yep.
And then like you'd have like that shear on that right side of it, on that second cut? I mean, not necessarily, but.
On the right side, I mean, the right side is always going to look like this. And the left side is always going to be all the way at the end of your member.
Okay.
And then there could be different stuff in between on the different cuts. Okay, so now we're going to go Newton's second law. And it says we have 707.1, 707.1. Those are the forces on the left. Plus T0 plus 0 negative V is equal to zeros. And you can solve these and you get that T is equal to negative 707.1 and V is equal to positive 707.1. And then we'll do the moment equation, and my about point is always going to be all the way at the left end. So if we're adding up the moments now, we have the couple on the left end of positive 707.1. The two forces don't produce any moment over there because that's our about point. Then we have, one thing, let me write in the dimensions here. This dimension is 0.5 meters. Okay, so now we'll add in that bending moment M. And then we'll also include the moment that's produced by that force V. So that V has a moment arm of 0.5. It has a magnitude of 707.1. It's acting down, so that downward force would make this rotate around the about point clockwise, so we want the negative. And then this is equal to 0. And so we have 707.1 plus m minus 353.5 is equal to 0. And so the bending moment is equal to negative 353.5. Any questions about that? So this is the rotational Newton's second law about the z-axis. And then the last thing we have to do is rotational Newton's second law about the x-axis. And so for that one, the only moments about the x-axis are the negative 500 on the left end, and then the fancy t on the right end. And so those add up to 0. And so we get that our internal tension, our internal, not our tension, don't make that mistake. Our internal torque, T, is equal to positive 500. Okay, any questions about that? That's for that specific point. So now what we're going to do is we're going to generalize this calculation. And we're going to calculate those internal loads for every horizontal location as functions of x. Okay, so I'm going to start by just drawing a few free body diagrams. So let's say various cut free body diagrams. If the right end is 1 millimeter from the wall, then our free body diagram looks like this. We have our force of 707.1, our upward force of 707.1, our bending moment on this side, I guess I'll do it like this, this was also 707.1. And then our torque on the left end of 500. And then on the right end, we have our internal tension, our internal shear force, our internal bending moment, M, and our internal torque, fancy T. If the right end is 0.4 meters from the wall, we have the horizontal force on the left of 707.1, the upward one of 707.1, the torque about the z-axis from the wall of 707.1, the torque, the couple of 500, and then over on the right end, we have the tension, the shear force, the bending moment, and the torque T. Bless you. Okay? And the thing to notice about these is that those free body diagrams look exactly the same. The only difference is that the length of the piece is different. Okay, so if we can represent the length of the piece as just this general value x, we can calculate both of these at the same time. Okay, let me do one more just to make it super boring. If the right end is 999 millimeters from the wall, then this looks like you have almost the whole beam. Over here you have the same forces. You have the same moment couple about the z-axis. You have the same couple about the x-axis. And then over on the right end, you have the internal tension, internal shear force, internal bending moment, and the internal torque. And so what I'm trying to get at is no matter where you make that cut, the free body diagrams look the same. The only thing that changes is the length, okay? So each free body diagram is exactly the same the only thing that changes is the length. So instead of doing infinitely many cuts, which takes a long time, I mean, you could do 100 cuts and assume that the functions are going to be smooth in between, and just do 100 actual cuts at different points, But instead, we're going to just do one cut. And we're going to represent the length by x. So this would be x equals 0.001 meters. This would be x equals 0.4 meters. this would be x equals 0.999 meters. We're just going to do one, and that x stands for all of those at the same time. Okay. So, okay. Our free body diagram. I'll just choose a representative distance, but we just computer. We just know that this distance is x. We're going to calculate everything in terms of that x. And now everything else we put on this is the stuff that's the same for whatever cut we choose. So we know we have the 707.1 horizontal, 707.1 vertical. The couple about the z-axis of 707.1, the couple about the x-axis to the left of 500. And then on the right end, we have our internal tension, our internal shear force, our internal bending moment. We don't know the value of that. That's M. And then our internal torque, fancy T. And like always, we're going to calculate our moments around this point. You don't have to. I mean, you can, in any statics problem, you can do your moments about any point you want, but this is the one that makes the math the cleanest. You can try it, or you can just trust me, you know. So Newton's second law now says 707.1, 707.1 plus T0 plus 0 negative V is equal to zeros. And so you get that the internal tension is negative 707.1, and the internal shear force is positive 707.1. Okay, so that internal tension comes out negative. Does that mean that this thing is in tension or compression?
Compression.
Yeah. So the negative means that this is compression. And then we'll do our moment equation about the z-axis. And this is the one where in this problem we're going to see that x come into it. The forces on the left end don't produce a moment. You do have the couple of 707.1. And then you have the bending moment on the right end. And then you have the moment produced by that shear force. So that's plus or minus a moment arm of x, because x is the length of this piece, times the shear force. And that's equal to 0. If that shear force is acting in that direction, would it make it rotate clockwise or counterclockwise around the red dot? Clockwise, so we want the negative. And so now I'll simplify this. We have 707.1 plus m minus Vx is equal to 0. Now I can substitute in the V value that we know. So we have m is equal to 707.1x minus 707.1. Any questions about that? So these Oh, and we didn't do the torque yet. All right, so Newton's second law about the x-axis. We have negative 500 on the left end. Nothing else produces an x moment except that external torque T, that internal torque T. And so this tells us that that internal torque T is equal to positive 500 Newton meters. Everything is constant except that bending moment. So let's think about what that means. So if we plot this bending moment as a function of x, our beam is 1 meter long. When x is equal to 0, so basically what we're talking about is what is that bending moment when this, when our cut is like an infinitesimal sliver? What's that bending moment? X is equal to 0 in that case. So we have, at that point, why did I put this? I want bending moment. So we're graphing bending moment versus x. Plug in x equals 0, you get negative 707.1. It's a linear function. Plug in 1 for x, and you get 0. And so that bending moment at the left end is negative 707.1, and it gets smaller and smaller until it's 0 at the right end. None of the other ones are worth graphing because they're all just constant. Any questions about that? Okay, so the key thing here is in this example, we just needed one general cut because all the free body diagrams are the same, you know, qualitatively the same. When do you need more than one cut? So when do the free body diagrams of the cuts change? Well, that happens anytime you have point forces. Point couples. Or anywhere that a distributed load function changes. Okay, so next time we'll get into cases where we have multiple cuts and we'll start talking about distributed loads. Does anyone happen to remember the checks on these things? The derivative checks?
Yeah, the derivative of m is v.
Yeah, so dm dx is equal to v. And then do you remember the other one related to distributed loads? So if you have a distributed load function q of x, negative dv dx is equal to the function q. So I just put those in parentheses. Remember that we'll get to those things eventually. Okay, that's it for today. See you Friday.
Kind of random question.
Yeah.
I don't understand how torque can exist in 2D.
Yeah, well, okay. Everything's happening in 2D except that torque, really. I mean, it's not really in 2D.
Oh, okay.
It's really,
It's like this. Twisting.
Yeah, it's really like a beam. Okay.
yeah, it's really, twisting around like that. I don't know.
Okay. Yeah, so we're just, okay. So we're representing it.
I'm just drawing it in 2D, yeah, but that twist is happening, yeah, like in a different plane.
Okay.